Today we're going to solve a problem involving AC circuits and complex impedance. Here's our problem. A sinusoidal voltage source with V effective of 110 volts delivers electric power to an impedance of Z equals 10 plus J8 ohms. We need to find the current delivered, the power delivered, and the power factor. Let's start by drawing our circuit. We have a sinusoidal voltage source with an effective value of 110 volts, and we have a complex impedance of 10 plus J8 ohms. The impedance consists of a resistive part of 10 ohms and a reactive part of 8 ohms. Since the reactive part is positive, this means it's an inductive reactance. To solve this problem, we'll need to work with complex numbers to represent our impedance and the sinusoidal voltage and current. Let's first understand the impedance. The impedance Z equals 10 plus J8 ohms, where 10 is the resistance R and 8 is the inductive reactance X underscore L. We'll represent our voltage as a phasor with the effective value of 110 volts and an angle of 0 degrees, since we can choose the voltage as our reference phase. Now let's find the current. According to Ohm's law for AC circuits, the current equals the voltage divided by the impedance. Since we're working with complex numbers, we divide the voltage phasor by the impedance phasor. The current magnitude will be 110 volts divided by the impedance magnitude of 12.81 ohms, which gives us approximately 8.59 amperes. The current angle will be the voltage angle minus the impedance angle, which is 0 degrees minus 38.66 degrees, giving us negative 38.66 degrees. This means the current lags the voltage by 38.66 degrees, which is typical for an inductive circuit. Next, let's visualize this with a phasor diagram. Here we have the voltage phasor along the positive real axis, since we chose it as our reference with 0 degrees. The current phasor has a magnitude of 8.59 amperes and lags the voltage by 38.66 degrees. This angle between voltage and current is the same as the impedance angle, and it's crucial for determining the power factor. Now, let's calculate the power delivered to the impedance. In AC circuits, the real or active power P in watts is given by the product of the effective voltage, the effective current, and the cosine of the phase angle. Substituting our values, we get 110 volts times 8.59 amperes times the cosine of 38.66 degrees, which gives us approximately 738 watts. Finally, let's find the power factor. The power factor is defined as the cosine of the phase angle between voltage and current. In our case, the power factor equals cosine of 38.66 degrees, which is approximately 0.781. Since our circuit is inductive, the current lags the voltage, so we have a lagging power factor of 0.781. Let's summarize our results. For a sinusoidal voltage source with an effective value of 110 volts delivering power to an impedance of 10 plus J8 ohms, the current delivered is 8.59 amperes, lagging by 38.66 degrees. The power delivered is 738 watts, and the power factor is 0.781 lagging. Understanding complex impedance and phasors is crucial for analyzing AC circuits. The physical meaning of these results is that in our inductive circuit, the current lags behind the voltage, and only 78.1% of the apparent power is actually used to do useful work. The rest is stored and released in the magnetic field of the inductor. Thank you for